Welcome back to ECE 501B. I'm entitling this lecture Basis Vectors, Spanning Sets and Linear Independence. And we will learn that we can create basis vectors from spanning sets and linear independence. And our goals today are really to follow up briefly on the consequences of the linear dependence lemma that we talked about last time. In particular, Theorem 2.6 lets us know that the length of any spanning set of vectors is always going to be greater than or equal to the length of a list of linearly independent vectors in that vector space. Proposition 2.7 says that if our vector space V is finite dimensional, then any subspace of V will be finite dimensional. And that seems to make sense. And those are the two consequences that we will present again in a few minutes in this lecture. The main part of this lecture is actually dealing with basis vectors. That's the plural, B-A-S-E-S. And those vectors, essentially, the thing to keep track of is they have two properties, a set of basis vectors. One is they need to span the entire vector space, and that set of vectors that's forming a basis that set needs to be linearly independent, or all of those vectors in that set are linearly independent. Once we have that understanding of what forms a set of basis vectors, then we can start talking about creating a basis set or a set of basis vectors, and we'll do that in a couple of different ways. We can do it by reduction, meaning we could start out with a large collection of vectors that span the space. So we now have this really extra collection of vectors in a spanning list. We can reduce that spanning list to create a basis. We're assuming then that initially that entire set of spanning vectors does span the entire vector space. Then by reduction, by throwing some of those vectors away, we can reduce down to a basis set, or we can build up by extension. If somebody gives us a vector space and a few vectors that are linearly independent, but yet they don't yet span the entire space, then we can extend that original set of linearly independent vectors into a set of basis vectors. That's what we want to cover today, which is to follow up a little bit on the linear dependence lemma and then spend the rest of our time dealing with vectors that form a basis, or how do we derive basis vectors from either a spanning list or a set of linearly independent vectors. Getting back to the linear dependence lemma, there's a couple of results. Theorem 2.6 states that in a finite dimensional vector space, then it makes sense to talk about a number that represents the length of that vector, or that represents the size of that vector space. The length of every spanning list of vectors, remember a list is a finite number of vectors, and the length is just how many vectors are in that spanning list. The length of every spanning list of vectors, how many vectors are in that spanning list, is greater than or equal to the number or the length of every linearly independent list of vectors. You give me a vector space, and then if you say, oh, here is a list of vectors that span that vector space, then the number of vectors in that list is greater than or equal to a number of vectors that are linearly independent in that vector space. Or you could give me a set of linearly independent vectors in that space, and I could give you many, many more vectors that would still be spanning or form a spanning set for that vector space. The second fallout or consequence of the linear dependence lemma is that every subspace of a finite dimensional vector space is finite dimensional. And remember that a subspace is effectively a subset, and so it sort of makes sense intuitively that if you start with something that's finite dimensional, anything that comes from that something must not get any larger in size or in dimension. And so that result or that proposition is intuitively, I hope, somewhat clear. Let's now start with the main focus of today's presentation, which is really basis vectors, and the plural is bases with an E. I'm going to now say a basis, which is just one set, and I like to maybe think of this as it's maybe hard to distinguish bases with an E and bases with an I. If we think of I as an individual or one, maybe that will allow you to distinguish between which of these words corresponds to the plural or a collection of individual basis vectors, where the basis vectors with an I is just one set of basis vectors, and a collection of those, if you needed them, which they can exist, would be the plural of with the basis of an E. A basis of a vector space V is a linearly independent list of vectors with one more property, and that property is that those vectors indeed span the entire vector space V. So a basis of a vector space needs to be a set of vectors that spans the entire space, and those vectors that are in the basis set need to be linearly independent. You don't want any redundancy, or a set of basis vectors does not have any redundancy. What are some consequences of having a basis set? It actually allows us, or it provides, a coordinate system for that vector space. Which leads us into proposition 2.8. Any element of a vector space V can be expressed or is expressible as a unique, and that's what's nice about this basis set of vectors, as a unique linear combination. That's playing on the fact that we do not have any redundancy in a set of basis vectors. Any element of V is expressible as a unique linear combination of basis vectors. And remember that the length of the list, a list is some finite collection of elements or objects, and in this case it's a list of vectors, and the length is just the number of those vectors in that list. the length of the list of basis vectors is in fact equal to the length of the shortest or the fewest number of vectors in a spanning list. There we've thrown out all of the redundancy in our spanning list is as small as possible. And remember the result from the linear dependence lemma, or one of the consequences of that, is that the length of a set of linearly independent vectors in a list is always less than or equal to the length, or the number of vectors in a given spanning list, where the spanning list is spanning the entire vector space. Now, a result of that inequality relationship basically says that since a basis, a set of basis vectors, I'm just shortening that sin to a basis, since the basis is both linearly independent and spanning, then we actually have the equality in that inequality condition. Equality must be true. Since that's the definition of a basis, it's consisting of a set of vectors or a list of vectors that span the vector space, and that list is a collection of linearly independent vectors. And since we know that the length or the number of vectors in a linearly independent list is less than or equal to the length of any spanning list, then in order for us to end up with a basis set of vectors, those lengths have to be the same. One thing to keep in mind is that for a given vector space, generally there's no unique set of basis vectors, or there's no unique basis. In other words, there's many shortest spanning lists. If we had a three-dimensional vector space, you might come up with many different three-vector sets of, or three different lists, or many different lists of three vectors that form a basis for that particular vector space. Let's look at something that's easily seen or visualized, which means let's look at a real two-dimensional vector space, essentially the xy plane. So now if we have the xy plane, and now somebody hands you two vectors, let's say one of those vectors is 0, 1, and the other is 1, 0, that collection of vectors, or that list of vectors, is actually a basis. Why is that? Well, in this case, we have one vector. The first vector is giving us this point 0, 1 if we consider this direction, let's say, to be the second coordinate or the y coordinate, and this horizontal coordinate being the first coordinate in those ordered pairs, then this, let's say, is vector A, and here, let's say, is vector B. Those two vectors are, I hope you can see, linearly independent, and they span, or you can get to any location in that two-dimensional plane by a linear combination of those two vectors. Maybe I should have called them something that we've been calling them, let's say v sub 1 and v sub 2. This particular collection or set of vectors actually forms, or this form, with a unit length in one direction and a unit length in the other direction, and we only have two directions. This form is called the standard basis. And now if we wanted to, we could get to any point in that vector space, which is a real xy plane, by any linear combination of vectors v1 and v sub 2. If we said, oh, what if we wanted to reach this particular point given by the vector 1, 1? Then that's possible if we take 1 as A1 and 1 as A2, and in fact that now gives us 1 and 1. So that now A1 is equal to 1 and A sub 2 is equal to 1 to be the scalars that scale V1 and V2 to produce that, let's say, arbitrary point 1, 1 in this two-dimensional real vector space, or in the xy plane. I don't want to necessarily mislead you into thinking that we always have to be dealing with an orthogonal or a standard basis set. What about another set of vectors? Let's say 1, 1 and minus 1, minus 3. And we want to know, would that actually be a basis of V? Again, we're assuming that V is our xy plane. The first point is now, or the first vector is actually this particular vector that has coordinates 1, 1. The other vector now has coordinates of minus 1, minus 3. And I hope it's clear from that sketch that indeed those vectors are not in line with one another. They are not orthogonal, and we will learn what orthogonality means later, but it does still form a basis because these two vectors are linearly independent. They don't line up with each other. They're not orthogonal, so they're not forming a standard basis, but they still create a set of vectors that we could use as a set of basis vectors. For example, what if we wanted to now find the same point, 1, 1, that we had in the earlier example? We want to know, how do we combine V1 with V2 in order to generate a new vector 1, 1? Well, in this case, it's somewhat trivial. We can just pick B1 to B1 and B2 to B0, we do not need any component in the direction of the second vector, and that now allows us to say that B1, B2, if we wanted to form those coefficients in some vector, is now 1, 0 would correspond to a vector 1, 1 using these two vectors V1 and V2 as the basis for that particular vector space V. Let's look at some other examples. Suppose that somebody now gives you the following: 0, 1. And they want to know, is this set of vectors a basis? Here's X, here's Y. In this particular case, we have a vector that is 0 horizontally and 1 vertically. And now we want to know, is it linearly independent? Yes, it's definitely linearly independent. There's the only one vector in there. And does it span all of this two-dimensional space? And in fact, it does not. So this particular vector, or this list, is not a basis. And the reason is we cannot get to any point in the horizontal direction. It doesn't span all of R2. And I hope you can see that you can't get to this hypothetical point that we've been using. Maybe I should use the same structure of my vectors. Can't get to 1, 1 using 0, 1. We can get to any vertical location on the y-axis, but we can't go left or right in that two-dimensional space. One more. Suppose somebody gives you the following list of vectors: 0, 1, 1, 0, and 1, 1. And they want to know, is this a basis of our vector space V? Again, the xy plane. That list contains a spanning set of vectors, but the vectors are not linearly independent, since there is some dependency among those. So this particular list of vectors is not a basis. If we were to sketch that again, then the first vector is again right there. Let's say that's V1. V sub 2 is over here, and V sub 3 is right there. And I hope it's clear that there is some dependency. We could write the vector V sub 3 in terms of V1 or V2, V1 and V2, or we could write V1 in terms of V2 and V3, or we could write V2 in terms of V1 and V3. So these vectors are not linearly independent. We can find an equation a1v1 plus a2v2 plus a3v3 equaling 0 when those a1, a2, and a3 do not necessarily have to equal 0 themselves. Or points in R2 now don't have unique representation, since we can always add 0 to any expression and not change that expression, and 0 now can be some linear combination of v1, v2, and v3, so we do not have a unique representation for any point in the xy plane. Points in R2 don't have unique representations as linear combinations of these three vectors, 0, 1, v1, 1, 0, v2, and 1, 1, which we were labeling as v sub 3. I hope now you have a little bit of an understanding, at least in this two-dimensional setting, of what constitutes a set of basis vectors. Now let's look at what we can do if we started with a spanning set or a linearly independent set. How can we create a basis from those particular starting points? Theorem 210 tells us how we can reduce or throw away or eliminate vectors that are linearly dependent. In particular, Theorem 210 says every spanning list in a vector space can be reduced to a basis of the vector space. We can show that or prove that in the following way. Suppose we are given a list of vectors that we're going to say we're denoting that list by the set of vectors B, v1, v2, up to v sub n. Given a list B of vectors that spans the vector space V, and we are going to assume that it is not a basis, but is not a basis. If it spans the vector space and it's not a basis, that then says we have some redundancy in that list of vectors. From the definition, of basis vectors, B must be a linearly dependent set of vectors. Because of that, we can now express some of those vectors in terms of other vectors in that set. From before, a linearly dependent list must contain an element that is expressible as a linear combination of the other elements. We can find some coefficients that we can now rewrite one of the elements in that dependent set in terms of some of the other vectors in that set. And from our knowledge of the linear dependence lemma, we can then throw that vector away without compromising our ability to span the vector space. The linear dependence lemma shows that we can delete this element that we've now written in terms of other vectors in the space. We can delete this vector without reducing the span of the list. So now we throw that vector away. The resulting smaller list, this new list, or if this new list is linearly independent, by that we can't find any vector in there that can be written as a linear combination of any of the other vectors in that list. If this new list is in fact linearly independent, we've now generated a basis by throwing one of the vectors away. And we can stop. If we find that the list that this reduced list that we've created still has some dependencies, then we can do the same thing that we just did. We can repeat the process and write one of the elements as a linear combination of the others and discard it. If the resulting list is still linearly dependent, we can repeat the process, and because we know that we're working with finite dimensional vector spaces, or this set is finite dimensional, eventually we can terminate this repeating process. For example, suppose we look at a set of vectors that we've already dealt with. Take the list that's 0, 1, 1, 0, and 1, 1. We know that that particular list indeed does span all of the xy plane, or R2. But we know also that it's not a linearly independent list, but it is not a basis because it's not linearly independent. We can then select one of those vectors and see if we can write it as a linear combination of the others. In this case, it's pretty clear that we can select the third vector in that list, since we can rewrite that in terms of the first two vectors. Then the resulting list that we are left with is in fact a list that's spanning all of R2, and it's linearly independent, and for that reason it does form a basis. Now, a corollary to theorem 210 is the following. Every finite dimensional vector space has a basis. Or we can now create some coordinate system for any finite dimensional vector space. And I hope we can see that, because now we could just start randomly creating vectors, producing a spanning list, and then from theorem 210 we can discard those that are linearly dependent until we get down to the minimal spanning list, which is a set of vectors that's both spanning the vector space and linearly independent. And so now we have a basis for that finite dimensional vector space. By definition, every finite dimensional vector space has a spanning list, and it could have many such spanning lists, but that's coming to us from the definition of something being finite dimensional. And now we can, from that spanning list, start tossing things away based on theorem 210. We just proved a basis can be generated and we were saying we were doing that by reduction, or eliminating redundancy in our vectors, or in our list of vectors. A basis can be generated from any spanning list. Let's now look at the other direction that we can pursue. We've now examined how we can reduce. Now let's see if we can build up or extend a smaller set of vectors into a basis. So every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis. Now we are building up instead of throwing away. Proof: given a linearly independent list, let's call that B, of vectors in the vector space V. And to make this useful, let's assume that that linearly independent list is not yet complete, or it doesn't span all of the vector space, and so those vectors are not a basis of V. So let's say that B is this set again, V1, V2, up to V sub n, but now it's not yet enough to be a basis. Now, from the definition, of a basis, B must not span V. Otherwise, it would be a basis. It's linearly independent. The only other property of a basis that it's not satisfying, or that must not be satisfied if it's not a basis, is that it must not span V. If that's the case, then let's just select another vector from the vector space that's not contained in that list or is not in the span of that list. So select an element. Let's call it U from the vector space, such that U is not capable of being written as a linear combination of those vectors v1, v2 through v sub n. Now, once we have that new vector or element from the vector space V, let's form a linear combination. And now we have U is equal to V1 plus V sub 2, let's say alpha 1 V1. Well, we wouldn't even have to scale these. We can get all of that in with our next piece, plus Q. We have U, we have all of the V's. We can solve for Q. Q is now U minus V1 minus V2, etc., down to minus V sub n. And we know, because this is a vector space, that Q belongs to that vector space, since the vector space is closed under addition. Now what we can do is we can actually put Q, which is a vector, into that previous list of vectors v1, v2 through v sub n. So now introduce or add Q to the list B. So that now we are sort of redefining B. We're just augmenting it, but we're going to continue to use the same B to represent this new set that now contains one more vector, which the vector now is Q. We now need to check and say, or see, if B now spans the vector space V, then B, or it's a basis of V, and we are done. We have the other possibility: if B does not span the vector space V, then we just repeat the process with this n plus 1 set of vectors and find another vector that's not contained in that list or in the span of that list, and now we get, let's say, a Q1. So we just repeat the process. And because we are dealing with finite dimensional vector spaces, we know we only have to do this a finite number of times, this repetition. Let's look at an example. where this example is showing that we can extend, or we can build, or building a basis from a linearly independent list or set of vectors. Suppose that B starts out as a collection of three-dimensional vectors. And let's say that B starts with just two vectors. And our vector space is this three-dimensional real vector space R3. I think it's clear that we're not capable of spanning or creating anything in the z direction with those two. They are linearly independent, those vectors in B, but they do not span all of R3. Let's now just pick a vector that's not contained in the span of V. And now we can write U, which is 5, 6, 8, as a linear combination of V1 plus V2 plus Q, and I will label each of the three components in Q, Q1, Q2, and Q3 are each of the coordinates of Q. Now we can see that Q1, Q sub 2, Q sub 3, in order to produce U, Q1 needs to be 4, Q2 needs to be 5, and Q3 needs to be 8. That is in fact in R3. Now we can create a new spanning list where B, again, we're reusing the labeling on that set. Now we're expanding that, and now it is made up of the first vector V1, the second vector V2 of the initial set, plus a new vector Q. And I think it's clear from this set that now the span of B is in fact all of R3. So now you should be comfortable with being able to create a set of basis vectors, and what we need is we need those to be linearly independent and span the entire vector space. We know how to reduce a spanning set into a basis, and now we know how to extend a linearly independent set of vectors into a basis. We will pick up from here talking about dimension and state some of the properties of dimension. We've sort of been using that when we talk about lengths of these sets, but that will then help us finish up Chapter 2 of Axler in the next segment.